Well, hello Internet, and welcome to part 5 of my time series forecasting tutorial series. In this tutorial, we've been talking a lot about ARIMA. This time, I'm actually going to show you the fantastic predictions it can make, and I'm going to cover a whole bunch more, and I have a lot to do, so let's get into it. Alright, so like always, everything's available in the description on GitHub, and these are exactly the same imports as always. So, now it's time to make some predictions with ARIMA. What I did was I went and actually saved my Pittsburgh weather temperature information into a CSV file, and we're going to be using this over the course of this video. But I'm going to need to import a couple new libraries because I'm going to be doing a lot more things. So I'm going to Stats Models, TSA, ARIMA, Model, and I'm going to import ARIMA and ARMA and ARIMA results. We might not get to every one of these in this video. I am going to, of course, have more videos coming because there is so much to cover. And ARMA results. Okay, what else are we going to need? From, again, Stats Models, Graphics, TSA Plots, and Import, Plot, ACF, and Plot PACF. And you may need to do pip install in your terminal or your command line because we're using Pyramid ARIMA in this tutorial, so that's what you would type in. But I already have it installed, so then you're going to go here and say import auto ARIMA, and there you go. All right. So let's go and take this Pittsburgh weather information. Oh, let's take this guy, just throw it up there. All right. And here you can see everything plotted out. And this is on a monthly basis, and you can very clearly see, or now you can better see, I changed fig size here. You can very clearly see that this is most definitely seasonal data. All right, so that's very important to remember. Now, what Auto ARIMA is going to do for us is it is going to tell us what model we should use. All right, so I'm going to throw my Pittsburgh weather information in there, and I'm going to mark seasonal as true and trace also as true. Trace is just going to go and give me all of the pieces of data as it's checking them. All right, and there's a little error here. Don't worry about it. And if we come the whole way down inside of here, you can see this is going to be the requested model that we use. I'm going to use ARIMA, though, with the same exact settings in this situation. And I'll talk more about seasonal and ARIMA later. Okay, so this is the model we're going to use. Now, what I want to do here first is I want to split the data into a training as well as a testing set, like I have done many times before. Of course, we're going to want to know what the size is. So that comes out to 480. And then we will say train df is equal to pdf iloc. And then we go and put 80% multiply 0.8 times 480, and you get 384. So those will be the data points that we train on. And then we will test against real world data points to see how accurate we are. And then we say 384, like that. Okay, and that'll give us the last 20%. So what I want to do now is I want to create my model, and I'm going to use ARIMA and train df, and the order I am going to use is exactly what it told me to use, which is 2, 0, 2. Then I need to fit my model. So mod fit to get my results. And then I can go and get the summarized forecast, which is going to be the same as auto ARIMA. So res summary. And if I run that, you can see exactly what we have right here. And I've talked many times about what all of those things mean. And now what I want to do is go and get the predicted values to see how accurate my results are. So to do that, I'm going to go length of my training data, And then end is going to be the length of my training data plus the length of my testing data minus 1. And I can make my prediction now. So I'll say prediction is equal to, I can get rid of that so that doesn't distract us. And the prediction is going to be the results, call predict, start to end. And let's say we want to rename this ARIMA prediction. And then what we can do is come in and plot our prediction. So I'm going to say, get our data that we have, plot. I'm going to set my fig size equal to 16 by 8. And let's say that we want a legend. And then after that, I will print my prediction or plot my prediction. And let's also mark legend true for that. And as you can see, if we go and plot our real data or our training data, and then we actually make our prediction, you can see here in orange, that is the ARIMA prediction. It is pretty accurate. And you can go in there and zoom in and look at it and so forth and so on, but pretty impressive stuff. And that brings us to stationarity. Now, I've received a ton of questions about stationarity, and I'm going to go in here and analyze everything and show you a whole bunch of different ways to analyze stationarity and such. But basically, stationary data is going to have a constant slope or rate of change, however you want to refer to it. And the reason you're going to want to use them is because they are easy to analyze and they are very often required in many aspects of time series analysis. And the main thing to remember is that for a data set to be stationary, the data must have a constant mean as well as variance. And we can test this by splitting the data and then testing for mean and variance. So I'm going to say dset is going to be equal to, and go and get my weather data. Then what I want to do is I want to come in and get my midpoint. So I'm just going to say split round length of this data set divided by 2. And then I can say dset 1 is equal to, and dset, and split it right down the middle. Then I'm basically going to get the other half. Throw that in there, change this to dset 2, and then get rid of this and put it at the end instead. And then now what I'm going to be able to do is go and get my mean for the first part. So I'm going to say dset 1 mean, and then we'll do the same thing to see if the means and variances match up. Change this to that, and then throw that there, and we'll change this to variance 1, and then change this to variance. And this is my Pittsburgh weather data, what I'm playing with here. And the variance for this is 2, and then this is also 2. And you can see right here that the means for this data set are very close, as well as the variance is very close. Not perfect, but this is definitely data that looks stationary and data that is largely stationary in general. And the Dickey-Fuller test from before is going to show I have a test statistic. Let's go and run this. Well, I guess I have to go get that. All right, throw this here, throw that there, and run it. Okay, so there's our Dickey-Fuller. And it, like I said, I'll make sure it's in the GitHub repository. And after I run it, you can see right here that I have a test statistic of -6. And of course, the more negative this value is, the more likely the data is to be stationary. And if we come up here and actually go and get the size for this and run it, you can see the size comes out to 480. And a Dickey-Fuller lookup table at sample size of 500 says that we can be certain 95% that our data is stationary if the test statistic is less than -3.98 in all situations. Well, it's -6. So while not perfectly stationary, it is very, in 95% plus percent of the times, it is going to work for us. Now let's go and get some data that would not be true for us. Let's just go and comment this out. And let's go and get our flight data. So I'm going to go and get flight DF. And I'm going to come in here and plug this in as well. There we are. There's all of our flight data. And if I go and plot that out, you can see right here, it is most definitely not stationary. And I can go and run an ADF test on it as well. Paste that in there and get my flight data. And most definitely, whenever we come to the test statistic, that comes out as 0.81. And also, it has a p-value that is over 0.05, which shows that this most definitely is not stationary data, even though we can look at it and see that it isn't stationary. So let's come in here and analyze how we can make data stationary or more stationary. So what I'm going to do is I am going to use pandas to difference the data frame and make the data stationary. So let's throw this in here. So I'll go pdf dot diff and drop na, which is going to get rid of any empty spaces, and then I'll say diff and plot, and then also ADF to see if anything has really changed here. Dramatically anyway. Diff df, and you can see the results that we have here. So let's come back up inside of here and uncomment this, and let's comment this flight data. And you can see right here our test statistic is a -6. You can see here it is a -1. However, you can see the p-value is super tiny, -18 versus -7. All right, so by going and taking the difference, we were able to make our data more stationary. And you can see that it doesn't really look that much different. Well, let's go and change the fig size on it. And there it is. And here's the other plot. So this is much smoother, what we have here, while this is more jagged. All right, so what it's trying to do is get the variance more in tuned, basically. All right, so let's take a look at our flight data. And what we're going to do here is we are just going to set it up so that we get a stationary mean. So I'm just going to call this diff2 underscore df is equal to flight df diff again and drop na again. And we can go diff2 df dot plot, throw fig size inside of here like that. And then we can run an ADF test on it. Diff2 underscore df, comment this out, come up here, comment this out, and uncomment this, and throw fig size in here so that you can see exactly what changed, which is basically the mean changes. Okay, so previously we have this, then after performing the difference, now we have this. All right, so you can see we have an average mean across the whole thing. But very often when I make videos like this, one of the #1 questions I get is, how does that work? How does ARIMA figure out that to make that Pittsburgh weather data plot 2,02? How does it figure that out? So what I'm going to do here is I'm going to show you. All right, so kind of show you. I'm going to show you exactly what it's thinking. So what I want to do here first is check to see that if there's a seasonal component to my weather data. So I'm going to go seasonal, decompose. This is our weather data. And the model is additive. It's definitely not multiplicative. And then we can come in and get the results of that and plot it. And here you can see our results. Most definitely seasonal. I mean, there's no doubt. This is seasonal data. All right. So let's comment that out. Then what I'm going to do is I'm going to go AUTA, ARIMA, PDF. And this time, even though it says it's seasonal, I'm going to mark it as false, just so I can show you what it's doing. And I'm going to say trace is equal to true. And then say we want a summary. And you can see it's generating all those different values for us here. Okay, so what's it do? it comes down here and it tells us in this situation, even though I told it wasn't seasonal, it went and figured it out on its own. But it gave us our best model as 405 right there. Okay? So that is what it told us. So how does it know that is true? Let's come down here and let's think about that. So the first question we might have is, how is integration determined? Well, if we come in here and we run Dickey Fuller on this, boom. In this situation, we see our p-value is under 0.05. So whenever it's figuring this out, it immediately says, well, we don't need to do anything with difference. And hence, you can see with the results, right here, it did nothing with difference. All right, so that's how it figures that out. So then what we need to do is we need to determine which is more significant, autoregression or our mean average. Well, how we can do that is I talked about ACF and PACF in the past. We can throw this here. We can go PDF, and I'm going to say lags is equal to 60, and copy this, paste it inside of here, and then just change this to P and run it. All right, so here are our results. Now, if PACF is going to have a sharp cutoff, then we are going to add AR to our model. And there are between 2 and 5, and that's basically what we're going to then test for. And that's exactly what ARIMA does. It checks 2 to 5 values, and then it looks for our best results. So you may say, well, how exactly do we then determine what our MA weighting should be? Well, in the situation in which there was a slow decline, let me go and show you what that looks like because we don't have that situation here. So what I'm going to do is I'm going to go and get my Apple data, Apple DF, and lags, and set that for 30, right like this. And let's throw semicolons in here so it doesn't double print these. Well, in this situation, here's Apple. And you can see here a slow decline. Now, in a situation like that, it is suggesting that we use AR over MA. But this is not going to be true with our temperature data. And what that implies to us is that we need to test for MA values that are greater than AR. And basically, there's just a lot of guessing here. And that is basically the reason why we use ARIMA. So hopefully you guys see exactly the power of ARIMA and the accuracy of it. You have a pretty good idea of how it's making these calculations, and hopefully you understand stationary data more and the importance of it and how to convert your data sets to a stationary format. And like always, please leave your questions and comments down below. Otherwise, till next time.